Hi guys, so today's video is going to be on probability, and this is from the Year 11 course. There is no probability in the Year 12 course, but that's not to say that it can't be asked in the HSC. And what we find with the probability questions in HSC and trial questions as well is it very rarely is based on single stage experiments. It's mostly on multi-stage experiments, like generally only 2 stages. So we're talking about like flipping 2 coins or drawing 2 cards or choosing 2 people or something, which means we're going to be talking a lot about tree diagrams. And what I've found, and I'll explain this later on, is if you're good with tree diagrams and if you can construct them and read them and get the information from it, that's pretty much all you really need to know with probability when it comes to the HSC. So anyway, let's get into it. So first of all, let's look at the syllabus points. To review and understand the language associated with probability, theoretical probability, and relative frequency. So remembering the difference here is that theoretical probability is like what theoretically can happen. So me rolling a die, getting a 5 would be 1 out of 6. That's a theoretical probability. Whereas the relative frequency would be if I actually went ahead and rolled a die 20 times and 5 of them was a 5, then it'll be 5 out of 20. So relative frequency, otherwise known as the experimental probability, is once you've actually done a bunch of trials, you get that. Whereas theoretical probability is, just looking at what could happen. And so in some cases, you're not able to actually calculate the theoretical probability. So in which case, the relative frequency is kind of like the best estimate you can use. Anyway, so constructing a sample space. Remember, sample space is a list of all possible outcomes. It's not just telling you how many outcomes there are. Other than that, so reviewed probability is a likely chance of occurring, whatever. So this is an important one. All probabilities need to be between 0 and 1. Right? So that means when you're finding a probability, you can never get an improper fraction. The numerator must be smaller than the denominator. If that doesn't happen, you've definitely got the answer wrong. Also noting that if the probability is 0, that means it's not going to happen, and the probability is 1 is definitely going to happen. And further on from this, you can say the probabilities of everything need to add up to 1. So if you have like a sample space and you found the probabilities of all the things, but they don't add up to 1, again, you've made a mistake. And these are things that can all be applied when you're, doing tree diagrams. So next is we need to find the probability. So everyone knows how to do this. This used to be on the reference sheet, but it's no longer on the reference sheet anymore, simply because it's pretty obvious how to find probability, number of favorable outcomes over the total number of outcomes. And then also talk about complementary events. So the probability that an event doesn't happen is 1 minus the probability that it does happen. So the basic example would be the probability of me rolling a 5 is 1 out of 5. So the probability of me not rolling a 5 is 1 minus 1 over 5. So that becomes 5 over, I wouldn't say 1 over 5, 1 over 6. And so that means the probability of me not rolling a 5, the complement is 1 minus 1 out of 6, which is 5 out of 6. All right. So also be aware of this notation where there's like a little bar above it. That just means it's like the complement, the opposite. Now here's a big part of this, and the thing you really need to use arrays. Arrays don't really pop up too much, but mostly tree diagrams to determine the outcomes and the probabilities of multi-stage experiments. And remember, what a multi-stage experiment is you do one thing and then you do another thing. And that doesn't necessarily mean to be one and then the other. You could be choosing 2 at once or flipping 2 coins, but each stage is its own kind of action. And then solve problems involving simulations or trials of experiments in various contexts. Now, you wouldn't really need to do this in the HSC, particularly where you're like performing simulations and all that kind of stuff, because if we got you to do your own simulations during the HSC exam, everyone's going to have different numbers, so it doesn't really make sense for that one. But yeah, this is an important one. Recognize an increase in the number of trials produces relative frequencies that gradually become closer to the theoretical probability. And that's what I was talking about up here. the more, like, if you don't know what the theoretical probability is, then you can just do a bunch of trials and find the relative frequency. If I do it 10 times, that might be pretty good. If I do it 100 times, it's going to be even better because it's going to get closer and closer to the actual probability. If I do it 1,000 times, then it's going to be even better than that because, you know, the more trials you do, the better picture you're going to get of what's happening. So that might come up in like maybe a multiple choice question or something. And then lastly, so just solving a bunch of problems involving probability. And I think I'm just going to go over all this kind of stuff once we, look at some past HSC questions. So just going on to this last bit. So reference sheet and formulas. There's nothing in here. Like I said, that used to be on the formula sheet, but you don't need it anymore. It's pretty simple. And so what I'm just talking about in this little bit at the bottom is you can pretty much, I would say you can expect to have one tree diagram question in your paper. If not, so be it. But I think if they are going to ask a probability question in your HSC, good chance it's going to be based on tree diagrams. So make sure you're comfortable with drawing tree diagrams, or at least filling in a tree diagram that's half completed for you. Now, talking about tree diagrams is really important. Before we go any further, I want to talk about one thing that I keep mentioning, but I keep seeing the same mistake happen. So I'm just going to drive it home one last time. Whenever you're doing a tree diagram, always start at a single point, right? If you don't start at a single point, if you're trying to think of the 3 cases in the first stage straight away, I tell you, it just makes things a whole lot more complicated, or people make mistakes when they don't start at a single point. Fact of the matter is, whenever I see a student make a mistake when they're tree diagrams, a lot of the time it's just because they didn't start at a single point. So you're thinking about everything starts at a single point, and then maybe if I rolled a die or drew a card or something, then 3 things could happen. And then maybe out of these, and then so the idea is you don't write numbers at the end of these. So maybe I had like the cards A, B, and C. So I had A, B, and C. So don't write the probabilities here. The probabilities go on the branch. So this could be like 1 out of 3, 1 out of 3, and 1 out of 3. Okay. And then from there, for the second stage, this is me choosing the second card. I could choose B or C. Here I could choose A or C. Here I could choose, A or B. All right, and then this would be 1 out of 2, 1 out of 2. So the key thing here is, first of all, starting at a single point, and then you can kind of think at the start of every stage as like another single point here, another single point here, another single point here. And then at the end of each of these branches is the outcome for that stage. And then, so of course, the way that we do this from here is this is A, B, so that outcome is A, B. That's A, C, B, A, BC, CA, and CB. And then the way that we find the probabilities of each of these things is, this is 1 out of 2, so I'll do 1 over 3 times 1 out of 2, that becomes 1 out of 6, and so on. So when you find the probabilities of each of your outcomes that you find at the end of your tree diagram, you multiply down the branch, or across the branch if you want to think of it that way. Anyway, I'm just going to start going into these HSC questions now, because a lot of the things that I'm speaking about here will be better shown in a question. So let's start off with the first question that I've set here, 2001 question 25A. So we have 5 men and 3 women are living on an island, but not all will be able to stay. So this sounds like a survivor or something. If one person is selected at random, what is the probability that this person is female? Now, this is a fairly simple question. To start us off, just reading the question, we have 8 people, right? So 5 men, 3 women. So if one person was selected at random, what's the probability that a person was a female? 3 out of 8. No tricks there. Now, part 2. Let's let that focus. So 2 people are randomly selected to leave the island. Copy the tree diagram into your writing booklet. I'm just going to do it on here. This is back in 2001 where Standard Maths had a writing booklet, and then you would have to copy it in, similar to your trials. What we're going to, like nowadays, it will just say, here's this tree diagram, complete it. So that's what I'm going to do. And complete the diagram by writing the probabilities on all the branches. So if I chose, for the first selection, if I chose a female, this is obviously 3 out of 8, like we just wrote, and that means this is going to be 5 out of 8. Now going into the next one, the idea is now we're choosing a second person, and it's saying that 2 people were chosen at random. So from that you can infer you can't choose the same person twice. 2 people were chosen. So because we can't choose the same person twice, that means this is without replacement. We're not replacing the first person we choose. So if I chose a female first, there's 3 out of 8. So that means on the second choice, there's only 7 people and 2 of them are female. And then for the males, if I chose a female first, that means there's still 5 of the males from the start. So it's 5 out of 7. And similarly here, if I chose a male first, that means the 3 females are still there, but then there's going to be 1 less male, so 4 out of 7. And then if I wanted to go and write down what my sample space is, so my sample space is FF, FM, MF, and MM, right? So now this is our sample space. It's a list of all the possible things that can happen. So this is saying we choose a female first and a female second, female first, male second, male first, female second, male first, male second. And then calculate the probability that the selection includes exactly 1 female. So what we're doing here is we're looking at all the outcomes where there's exactly 1 female. And so note that this will be different if the question said at least 1 female. If the question said at least 1 female, that means we'd also have to be looking at this outcome because that's 2 females. It fits that condition. But if we're saying exactly 1 female, that means we're just looking at these 2. So like we said, all that we've got to do to find the probability of each of these is multiply down the branch. So we do 3 over 8 times 5 out of 7. Now, what I suggest you do when you're doing tree diagrams is don't simplify your fractions as you go along. Keep these as unsimplified fractions because it makes comparing and adding up all your fractions a whole lot easier later on because everything has the same denominator. So to do that, what I suggest you do is rather than going into your calculator doing 3 over 8 times 5 over 7, I suggest you do 3 times 5, which is 15, and then 8 times 7, which is 56. So 15 over 56. Now that might actually not simplify in the end. So if you just did 3 over 8 times 5 over 7, you got that anyway. But it's important that you can do that because seeing that everything's going to be 8 of 7, 8 times 7, 8 times 7, 8 times 7, 8 times 7, everything is going to be over 56, which makes comparing the different options a lot easier. Anyway, the other one that we're looking at is the other male than female. So it's 5 times 3 is 15, 8 times 7 is 56. So they just turn out to be the same probability anyway. So calculate the probability that it's at least exactly 1 female, or the probability of exactly 1 female. So remember we thought the idea is whenever you think of the word and, you're multiplying. So this is female and male, so I multiplied. Male and female, so I multiplied. But when I'm thinking of, I've got this option or this option, whenever you think of the word or, you plus. So it can be FM or MF. So adding these 2 together, so there'll be 15 over 56 plus 15 over 56, which is 30 over 56. And this is kind of why I tell you to not simplify the fraction, because they're both over 56, meaning that you can just add them together, add the numerators together, makes things easier. So that's that. And now if I can simplify, which again, I don't think I can simplify, I'll just double check to be sure. But I'm almost positive you can't. Oh, you can. Whoops. Obviously, you can divide by 2. That's duh. So at this point, you can go ahead and simplify if you want. That's fine. But I'm just saying, as you're going through the question, simplifying might not be the easiest thing or best thing. And lastly, part 3. So Antoinette is one of the women on the island. Before 2 people are randomly selected to leave, Antoinette calculates her chance of remaining on the island. She concludes that she has a good chance of remaining. Do you agree? And justify your answer. So what we're doing here is we're thinking about Antoinette, a particular person though. So what we're not doing is focusing on the male and female. This is kind of useless now. We're just thinking about this one particular person, Antoinette. So we could go ahead and draw a tree diagram again for this situation. So we can say that Antoinette stays or Antoinette leaves. So starting at a single point, stays, leaves. And then, so the probability that Antoinette stays after the first choice is 7/8. And that makes sense. I mean, if there's 8 people, 7 of them aren't her, and then 1 person is her, right? So we have this, and then this for the second choice, we're going to do this. So stay, leave. And then, so if she stayed on the first choice, 6 out of 7 to stay on the second choice, or 1 out of 7, and then this would be 6/7, 1 out of 7. So then from here, we're going to be looking at probability. So we want to make sure that she doesn't leave the island. So that means we need to avoid, we've got SS, SL, LS, or LL. So if she's to stay on the island, that means she can't get an L. She can't leave. So that means we're looking at this one. And then this is just simply 7. So 7/8 times 6/7. So that's 42/56. And that's your answer. So that's one way of doing this question, by drawing up a tree diagram and then kind of looking at which only option works. The other way that we could do this is we could just think of like stays. Well, the only way that this person can stay is if they're not chosen the first one and they're not chosen on the second one. So if you're not chosen on the first one, it's 7/8. And if you're not chosen on the second one, well, it's 6/7, because now there's 1 person left and 1 of them left. 1 of them less. So, and then from that, you just get 42/56, which you could also simplify to be 21/28, which also simplifies to be, what's that? 3/4. All right, so you get that probability. I think that's right. Let me just double check. 42/56. Yeah, 3/4. Okay, so we get this. Now, we found the probability of her staying, but that doesn't actually answer the question. The question is, do we agree and justify the answer? Well, here's our justification. So we just need to finish off the question. So therefore, yes, agree, because she has a 3 out of 4 chance of staying, or something like that. And then, so she has a good chance. A good chance can pretty much mean likely. All right, so if it's above 50%, if it's above 1/2, you can say it's a pretty good chance. It might not be a great chance, but it's a pretty good chance. Anyway, going on to the next page. So similarly, you look straight away, it's another tree diagram question. This is from 2005, and that's because tree diagrams pop up a lot. So Mohab owns 5 red and 7 blue ties. He chooses a tie at random for himself and puts it on. He then chooses another tie at random from the remaining ties and gives it to his brother. So what is the probability that Mohib chooses a red tie for himself? Very similar to the previous questions. We have 5 red and 7 blue, so there's 12 total. So if he's choosing one for himself first, so that's just going to be 5 out of 12. Very simple. Second question. So again, ignoring the fact that we don't need to draw in the writing booklet nowadays, we'll just have it and you can draw on here. So complete the tree diagram by writing the correct probability on each branch. So this is something you definitely should be comfortable with. So we have 5 out of 12 and 7 out of 12. So starting from a single point, but it's done all for you. And then, so now the idea is, again, this is without replacement because it's not like we're replacing that tie. So that means if we chose a red for himself, that means it's 4 out of 11 for his brother. And then it's 7 out of 11 for his brother, for blue. And then go from here. So if we choose a blue one first, that means we still got the 5 red ties remaining, and then there's going to be 6 blue ties remaining, and note they're all out of 11. And again, just to kind of reiterate, so the probabilities of each of these need to add up to 1. 5 over 12 plus 7 over 12 equals 1. 4 over 11 plus 7 over 11 equals 1. 5 over 11 plus 6 over 11 equals 1. This always has to happen. If it doesn't happen, you've made a mistake. And then, so that's the answer, and that's it. So complete your tree diagram and correct the probability in each branch. Done. Now we might as well write the sample space real quick. All right, and then lastly, so done. And then for part 3, calculate the probability that both ties are the same color. So we're trying to find the same color. So rather than trying to find the probability of each of these, let's just focus on all the ones with the same color. So we're looking at RR or BB. So again, this is rather than doing 5 over 12 times 4 over 11 in your calculator, do 5 times 4, which is 20, 12 times 11, which is 132. All right. If you put that into your calculator, that does simplify to be, what's that, 10 over 66, and then that can simplify further. The reason why we don't want to do that is because if we're also looking at blue, so this would be 7 times 6 is 42 over 132. So because they're the same denominator, I can just add the numerators, because now I'm looking, if they're the same color, that means it can either be red, or blue. So 20 plus 42 is, so probability both same color. That equals 62 over 132. All right. Just going to do these last two a little bit quick. So first of all, so we have a new test that's being developed for determining whether or not people are carriers of the Gaussian virus. So 200 people were tested, and that's kind of hidden in the question. So 200 people are tested, a two-way table has been recorded for these results. So we need to find the value of A. So this is our two-way table, so this needs to account for all the 200 people. So the missing number here is simply 200 minus 74 minus 12 minus 16, which equals 98. All right. Next, a person selected from the test group is a carrier of the virus. What is the probability that the test results would show this? So we're choosing from a person selected from the test group is a carrier of the virus. So we're choosing a person from this group. Sorry, give me a second. Person selected from... I'm just trying to interpret what this question is saying. So what I'm just going to say here is what this question is saying is a person selected from the group is a carrier of the virus. So that means we're choosing from the carriers of the virus. We're not just choosing out of everybody, we're choosing from the carriers of the virus. So here the carriers, normally we have this total column here as well. So this is going to be 86. There's 86 carriers in total. And then so now we have those 86 people. What is the probability that the test will show that they're the carrier of the virus? Well, there's 74 of the carriers. 74 of them are testing positive. So probability would be 74 over 86. Okay? And then you can simplify that. And then lastly, the question is for how many people tested were the results inaccurate? So we're looking at inaccurate. So we're thinking, okay, it would be inaccurate if they were a carrier but was showing up as negative, or if they weren't a carrier but was showing up as positive. So we're either looking at these 12 carriers that were negative, or those 16 carriers that were positive. So it's just 12 plus 16 equals 28. So the key thing to this is just being able to read a two-way table, which you would have been doing for years now, and remembering that there could also be like these total columns and rows at the end as well. All right, last page. I'll just quickly go through these. So this is two multiple choice questions. A die has faces numbers 1 to 6. The die is biased so that number 6 will appear more often than the other numbers. The numbers 1 to 5 are equally likely to occur. The die was rolled 1,200 times and was noted that the 6 appears 450 times. Which statement is correct? So all the information we need is in this line here. This is what we're talking about, like theoretical probability can be estimated, because it doesn't tell you how more likely 6 is going to occur, but we can kind of make an estimate based on this information. So the probability of rolling a 6 is 450 out of 1,200, and that simplifies to be 3 out of 8. So that means there's a 3 in 8 chance of it being a 6, From that, we can also say the probability of it not being a 6 is 5 out of 8, and that's using the complementary events. So if probability of getting a 6 is 3 out of 8, then not a 6 is 5 out of 8. And we then, if it's not a 6, that means you're rolling a 1, 2, 3, 4, or 5, and we said that they're equally likely. So that means the probability of getting any other one, so probability of any other number is going to be 1 out of 8. Because if I got the 5 out of 8, and I'm just dividing that by 5 because they're all equally likely. So now we have this information. Let's look at what we could do. So the probability of rolling a 5 is expected to be 1 out of 7. No, we just calculated it to be 1 out of 8, so it's not that. The probability of rolling a 6 is 2 times as often as any other number. No, because it's 1 out of 8, but this is 3 out of 8, so it's not that. The probability of 6 is expected to appear 3 times. That is correct. That's the answer because it's 3 times as likely as everything else. But just to confirm, the probability of rolling an even number is expected to be equal to the probability of rolling an odd number. That's definitely not the case because 6 is happening far more often than everything else. So it means rolling a 2, 4, or 6 is going to happen more times than rolling a 1, 3, or a 5. So it's not that. So the answer is C. Then lastly, and this is a very easy question, I'd say, question 3 from 2005. It's just asking which one has the highest probability. And this is just showing like probabilities can be expressed in different ways. So if we were to write these all as decimals, this would just be 0.53, obviously. 17% is 0.17. 13 out of 25, that can be expressed as 0.52. Remember, you just chuck that into your calculator and press the SD button, and then here's 0.6 or 0.60. Just remembering that that's like not just 6, it's 0.60. So obviously the thing with the highest probability is 2DL, this one here. All right. Anyway, so hopefully that's useful. Again, just to reiterate, the most important thing you need from probability in HSC is tree diagrams. If you can do tree diagrams, you're probably going to be almost certainly good for probability. If you have any more questions that you want me to go through, be sure to send them. Thank you.